The remaining task is to find the orientations associated with our principal stresses. Before looking at those particular orientations, I want to explore another special feature of Morse circle. Let's look at our first stress point. It's associated with that red vertical surface. Let's combine the information that this red surface belongs to the point sigma x tau xy by simply doing a parallel translation of that surface through that point. We do a similar thing with the blue surface, which is in our case a horizontal surface. The point belonging to that stress state is sigma y and minus tau xy, and we simply do again a parallel translation of that surface through that stress point. These two lines meet on Morse circle, and that point where they meet, we call this one the pole of the current stress state. We conclude that the pole is always located on Morse circle, and that any lines parallel to a surface through a point go through the pole. Reversing this argument, we conclude that any line from the pole through a point on Morse circle defines the surface on which the associated traction will live. That means all we have to do is draw lines from the pole through our two principal stress points to find the orientations associated with those principal stress points. Let's not forget that the marked points sigma 1 and sigma 2 actually represent a combination of normal stress sigma 1 and zero shear stress. Finally, we can interpret the 2 points sigma 1 and sigma 2 as two orthogonal surfaces, which in turn define a stress block. The orientation of the principal stress block can be found directly from the figure. All the angles in this technique are the true angles, so there's no need for factor of 2 as in the traditional double angle approach.